Calcium chloride. Calcium chloride is a compound made of these parts. One calcium atom for every 2 chlorine atoms. Those are put together like this. There are both calcium ions and chloride ions in ocean water. In the history of the Earth, ocean sea level, the height of the ocean, has been both 300 feet higher and about 300 feet lower than where it is today. At the higher times, it has flooded regions that are now above sea level. And when the ocean level went down and receded, the ocean water got stuck, and eventually the ocean water that got stuck evaporated, and all of the salts that were dissolved in the ocean were left behind. That included compounds like calcium chloride. So in places in the world where seawater got trapped, and then as sea level went down, that trapped seawater evaporated, those places have huge expanses of salts, and those salts include calcium chloride. And there are regions of these salt flats in many different places across the world. Each of these salt flats contains many types of salts, but among them is calcium chloride. Calcium chloride when it forms, it can form a mineral called anarctite, and it forms especially in one place in Antarctica, around the Don Juan Pond. This is a pond that has liquid water even at temperatures below -50 degrees Fahrenheit because of how salty the water is. And this white dust that you see around this pond, this Don Juan Pond, includes an amount of naturally occurring calcium chloride. And you can see that in another view here, this white dust of naturally occurring calcium chloride. Humans use calcium chloride for a bunch of things. A major one is to melt snow in the winter on roads. Just like the water was kept a liquid at -50 degrees Fahrenheit in the Don Juan Pond of Antarctica, in the same way you can make snow salty, and therefore it will melt on roadways in North America. And so many trucks just sprinkle huge amounts of calcium chloride onto roads to melt the snow. Calcium chloride also absorbs moisture. It will absorb water, and so you can use it to dry things. A fancy way of saying that is it is a desiccant. It dries things out. So you can have these containers that are airtight and put a layer of calcium chloride on the bottom, and then put a little stand in there, and anything you want to dry out you can just let sit on that stand. And the calcium chloride will slowly absorb all of the water out of that object. That can be used for some practical purposes, like dirt roads. If you've ever seen someone drive down a dirt road, there's a cloud of dust that follows the car. And that degrades the road, and over time you have to replace that with new sand. If you sprinkle roads with calcium chloride, the calcium chloride will absorb moisture in the air, and you can see that will make the road look wet like this, even on a completely sunny day. And that moisture will help to keep the dust particles together, and that will prevent clouds of dust forming when people drive down these dirt roads, and that lowers the number of potholes by around 80%, sprinkling them with calcium chloride like this. Creatures need calcium in the ocean, creatures like corals and mollusks when they make their seashells. And so if you are running an aquarium and you want corals or sea fans or mollusks to grow in there, one of the things they do is they will throw some calcium chloride into that aquarium so that those creatures have the calcium they need to make their hard parts. Calcium chloride is added as an electrolyte to sports drinks, and it's used to flavor beers. This is a brewery. And it's also used to flavor cheeses, which are being made in this large vat here. It firms tofu curds, so these are soft curds of soybeans, and if you add some calcium chloride to that and let it sit, it will firm into tofu. And it also helps concrete to dry quickly. So for example, in the Pantheon in Rome, if you look at the famous coffered ceiling here with the oculus in the middle, this is concrete, and that concrete dries faster when you add calcium chloride to it. When you're thinking about the safety of a molecule, it's useful to summarize your thoughts and the considerations with these fire diamonds or safety squares. The blue diamond on the left represents a molecule's risk to your health. This is on a scale from 0 to 4, where 0 represents no health hazard, and 4 represents a quick death on exposure. Calcium chloride is a 2 on that scale. It can cause eye irritation and possible eye burns. That's because when calcium chloride absorbs water, it releases heat. So when it comes into contact with the water of your eyes, it will release heat, and that could burn your eyes. So when you work with it, you want to make sure you wear goggles. It can also cause skin irritation, and for the same reason, skin burns. Any moisture on your skin, the calcium chloride will absorb, release heat, and that can burn your skin. So when you work with it, you want to make sure you wear gloves and a lab coat. If you breathe in the dust of calcium chloride, it can cause severe irritation of your upper respiratory tract. It can be painful, and there too, because there's moisture there, it can cause burns and inflammation. So when you work with it, you want to make sure you work with it underneath a fume hood. An interesting measurement that communicates the toxicity of a molecule is the LD50. In any population, some people will be more frail, and others will be more robust. So the same dose of something that's toxic won't kill everybody. Instead, people talk about what kills 50% of a population. And that's the LD50. That's the lethal dose for 50% of people. If you give this amount of this molecule to people, 50% of them would die. For calcium chloride, that's around 1,000 milligrams per kilogram of body weight, and this is measured in rats, so it's an estimate for humans. The red diamond at the top represents the molecule's flammability. It's also on a scale from 0 to 4, where 0 tells you the molecule will not burn under any circumstances, and a 4 tells you the molecule is a flammable gas at room temperature. You can see that because calcium chloride is a 0, it will not burn at all. It will never respond to a spark. Any spark that falls on calcium chloride will just go out, so it has no flash point. And it will never spontaneously burst into flames, no matter how hot you get it. So it has no auto-ignition temperature. The yellow diamond on the right tells you about a molecule's instability or reactivity. That's also on a scale from 0 to 4. In this case, 0 means the molecule will not explode, and 4 means the molecule will explode at room temperature if disturbed. Calcium chloride is a 1 on that scale, not because by itself it is explosive, but because it releases a lot of heat when it's exposed to water. When it absorbs water, it can release heat. So if it's exposed to a lot of water all at once, or a lot of moisture all at once, it can release a lot of heat all at once, and that will simulate an explosion. Because the white diamond at the bottom is empty, it means there are no special considerations you have to think about when working with calcium chloride outside of the health, flammability, and instability considerations. Let's try to visualize calcium chloride. Calcium chloride is an ionic compound. That means that the atoms are not sticking together because they share electrons in bonds, covalent bonds. Rather, they're sticking together because they have opposite charges, and opposite charges attract. So calcium, here, it's a slightly larger atom, is completely positive. And each of the chlorine atoms, which are ever so slightly smaller than calcium, are completely negative. And they stick to each other because of their opposite charges. They stick to each other in a repeating array. You can see here that calcium atoms get stuck in between chlorine atoms, and those chlorine atoms get stuck in between other calcium atoms. So you get a sort of lattice. This lattice repeats on larger scales, and then even larger scales, until the molecule, the crystal, the lattice gets so large that we can see the molecule with our naked eye. And when that happens and all of the atoms merge together like pixels on a screen, we see, our brain creates the sensation of a white solid for calcium chloride at room temperature. That white solid is representing enormous populations of calcium chloride atoms. Once those atoms get together in an enormous population, that population takes on its own personality. The personality of a huge population of atoms is called the physical properties of that compound. You could look up physical properties for things like calcium chloride in a reliable handbook like the CRC handbook on the left or the Merck Index on the right. One physical property you could look up is the phase of a molecule. Is the molecule a solid, a liquid, or a gas? Well, at sea level, that will depend on temperature. And so, calcium chloride will be a solid if the temperature is below 1,427 degrees Fahrenheit. Notice that's an enormous temperature. That includes room temperature. If you get it hotter than 1,427 degrees Fahrenheit, but less than 3,515 degrees Fahrenheit, it will turn into a liquid. You could reach these temperatures on the surface of a stove. If you get it hotter than 3,515 degrees Fahrenheit, it will turn into a gas. As a scientist, you don't just want to think in terms of degrees Fahrenheit, you also, and especially, want to think in terms of degrees Celsius. So to say that again, calcium chloride will be a solid below 775 degrees Celsius. That includes room temperature. It will be a liquid between 775 degrees Celsius and 1,935 degrees Celsius. And it will be a gas above 1,935 degrees Celsius. You could separate calcium chloride from other things in a mixture by using these freezing or boiling points. You could, for example, cool the mixture down till calcium chloride solidifies out of it. And then you could strain calcium chloride out of that mixture. When you separate things based on their freezing points, it's called crystallization. Now this might seem strange because this is a really hot temperature. Where would you have this molten liquid where calcium chloride could freeze out of it? Well, that's actually really common in the crust of the Earth. When rocks go from the mantle to the crust, they go from being hot magma to being cold rocks. And when that happens, minerals like calcium chloride can solidify out of them and separate from the rocks as their own pure thing. Likewise, you could separate calcium chloride from a mixture by heating it up so that just the calcium chloride evaporates and nothing else does, and then you could theoretically catch that vapor and limit it to another container. When you separate things based on their boiling points, that's called distillation. A second physical property that's important to consider is solubility. Solubility is significant because it creates structure within fluids. Let's think about the solubility of calcium chloride in water at room temperature. Solubility really has to do with how charges are spread out over molecules. Water has partial charges on every atom of the molecule. As you can see, every atom in calcium chloride also has a charge. Notice also, this is to scale how much larger a calcium atom and chlorine atoms are than the oxygen and hydrogen in water. So if you were to look at this, you would say, well, the positive hydrogens will definitely be attracted to the negative chlorines. The negative oxygen will definitely be attracted to the positive calcium. And so you would expect calcium chloride to dissolve very well. And a lot of calcium chloride does dissolve, but it is not completely miscible. There is an upper limit. And that's because water is attracted to these ions, but these ions are also attracted to each other. So it's a sort of tug of war. The water wants to pull the atoms away from their lattice. The ions here attract each other. That wants to keep the lattice together. And in that tug of war, around 745 grams of calcium chloride will dissolve in each 1 liter of water. If you pour more calcium chloride into the solution after that, it won't dissolve. What will it do? That depends on the density. Density creates structure based on sinking and floating. More dense objects sink, less dense objects float, and that creates layers in our world, from layers in the core, mantle, and crust of the Earth to layers in the atmosphere of oxygen, more oxygen as you're at sea level, and then less as you get higher. The density of calcium chloride is 2.15 grams per milliliter. Compare that with the density of water. Water has a density of 1 gram per milliliter. So if you pour excess calcium chloride in water, it will sink to the bottom of the water and form a carpet of salt there. Hopefully this video has given you a deeper understanding of the compound calcium chloride.